Hello. In the previous two videos, I have talked about the logistic regression method, about the idea, the motivation, the theory behind it, as well as the cost function and how we can find a proper cost function using the method of likelihood. And in today's video, I will talk about the common ways we can use in order to build our classifier using either the gradient descent algorithm or the Newton's method. In order to start the topic today, I would like to refer that the logistic regression model has no closed form solution, and this is because the hypothesis behind the logistic regression is the logistic function, and the logistic function is classified in mathematics as a transcendental equation. Which means that it has no closed form solution because it includes the Euler number or the exponential component e to the power of minus w transpose x, and because this is an approximate value, accordingly there is no closed form solution for this class of equations. So in general there is no closed form solution for the cost function of the logistic regression model. Moving to the gradient descent algorithm, we have the same algorithm that we have used in both linear and polynomial regression methods that I have described in previous videos. The only change is within the update value. So here we will replace the derivative of the error function in the case of linear or nonlinear regression methods with the derivative of our cost function with our log likelihood function that we have computed in the previous video, and it is simply equal to minus 1 divided by n multiplied by the difference between y super I minus g of x super I and w multiplied by x super I, which I have mentioned before that this is the same derivative as the one of the error function of linear and non-linear regression methods. The only difference is with the logistic hypothesis g of x super I and w, which replacing the linear or non-linear hypothesis f of x super I and w in previous regression methods. So this is the only difference when we apply the gradient descent approach. Another point to take care of is that as you remember that I have mentioned that in classification problems we can either minimize or maximize the cost function. So in the case we applying gradient descent, we're trying to minimize the log likelihood function. So here we add a negative signal in front of the log likelihood function in order to properly minimize the error that can be generated by the classifier, and in order to optimize the performance of our classifier, as I have explained in the previous video. You can also use it the other way around. You can also maximize the cost function using the typical algorithm, but in this case we called it gradient ascent because we're trying to maximize the cost function, not minimizing it. And in this case we're using the plus signal, so we add the derivative of log likelihood to the previous value of coefficient in order to update and obtain a new value of our coefficient. So in this case we replace the minus value with the plus value and the algorithm will call now the gradient ascent, not gradient descent. So you can use both algorithms, and both algorithms, when used properly, will generate identical results. And by the way, I will add in the description below this video a link to the implementation to my GitHub repository, where you can find a Python implementation of all of these algorithms, and I'm encouraging you to download it, run it yourself, and try to understand the difference between both methods, between gradient descent and gradient ascent. In order, after computing the or after using the gradient descent or gradient ascent, how we can make predictions, how we can decide if the new observation is related to class 0 or class 1, for instance. In order to obtain the probabilities of y, or in order to make predictions of a target variable y, we need to solve the Logit equation. This is the ratio that I have talked about in the first video of logistic regression. You can refer also to it, and it is equal to the log of the probability of y equals to 1 divided by the probability of y equals to 0, which is equal to the e raised to the power of minus w transpose x. We can simplify the expression by saying that this is the log of p divided by 1 minus p, where p of y equals 0 equals 1 minus the probability of y equals 1. So we can write it simply in this formula, and we need to solve this expression for the value of b. And when you solve this expression with the value of b, you find that the b equals to the e minus e to the power of minus w transpose x divided by 1 plus e to the power of minus w transpose x. Once you have solved this expression using the outcome of both of the classifier, using the outcome of list of coefficients that you have obtained using gradient descent or gradient ascent, and your set of predictors x, then you can find the outcome of your logistic regression model in a value of 0 and 1, or in the value between 0 and 1. Now I will talk about another very practical way to use instead of gradient descent or gradient ascent. It is a very nice way to find the values of coefficients. It's called the Newton's method, and Newton method is a very popular method in calculus as well as in statistics, and it is a very fast method to reach the roots of a given function, like the function you see here, in a very small number of iterations. So suppose that we need to find the roots of this function, that we need to find when this function f of x reaches 0. So Newton have said that we can start at any random point, say x 1, for instance, at this point, and we can draw a vertical line from this x1 up to the point up to the curve, which it meets at point A, and at this point we can calculate the derivative of this of the function at point A, or just the slope of this function at point A. And when this tangent line interacts with the x-axis, it will reach out a value called x2. And it is definitely that x2 is closer to the root of the function to the x1. Now, if we want to find exactly where the value of x2 lies, it is simply equals to the x1 minus what we call the delta x minus this distance here, the distance between x1 and x2. And we can calculate delta x by finding the by dividing the value of f of x by the tangent value of f dash of x1. So this is the value of function f of x at point x1, and this is the first derivative of f of x at the value of x1. So if we manage to compute this ratio f of x1 divided by f dash of x1 and subtract it from x1, we can obtain the point x2, which is closer to the root of the function f of x rather than x1. And if we repeat this procedure for a few steps, then we can very shortly reach to the point where we obtain the value where f of x equals to 0. So we start at x1, we jumped to x2, is very close. Now we draw another vertical line and compute again f of x2 and f dash of x2. We obtain the f of x3. So after very few steps, we will reach a point where we knew that the f of x at this point equals to 0, and this is what we need to find the root of function f of x. So this is a very efficient way to find the roots of any function you have. And in our case, the case of logistic regression, the function that we're trying to minimize is actually the first derivative of the log likelihood function. So if we translate the same idea into our logistic regression model, we will say that the f of xk is corresponded to the L dash of w, which is representing the first derivative of log likelihood with respect to a vector w, divided by the second derivative of the log likelihood with respect to w. So we have before calculated the first derivative of the log likelihood, and now we will try to calculate the second derivative of the log likelihood. So the first derivative took this formula, and we learned in the previous video that it is identical to the first derivative of the error function of the linear regression model. The only difference is between the logistic hypothesis in the logistic regression and the linear hypothesis in the linear regression. So let's compute the second derivative of log likelihood function. It will be the derivative of this expression, y super I minus j of x super I and w multiplied by x super I with respect to the coefficient wj. Now if you want to calculate it, we will have here the derivative of x super I y super I, we multiply x super I 2 times here and here, minus x super I multiplied by by j of x super I and w. This term will be deleted, and we end up with this term, which is we will send the minus signal outside the summation, so it will equal to minus summation of the derivative of x super I, j of x super I and w. We will send the x super I outside the differentiation, so it will be minus summation of x super I of the derivative of g of x super I and w divided by the with respect to the coefficients wj. And if you remember from the last video, we have computed this expression particularly, and we found that the derivative of j of x super I and w with respect to wj is equal to g of z multiplied by 1 minus g of z multiplied by x super I, where g of z is our logistic hypothesis. So now when we substitute this value within the second derivative of our log likelihood function, we will get that the second derivative equal minus summation of x super I multiplied by g of x super I and w multiplied by 1 minus g of x super I and w multiplied by x super I transpose. And this formula that you are seeing here is called the Hessian or the Hessian matrix, and we can write it into a more compact form or a more matrix form like this. We can say that the capital H super I equals the matrix X multiplied by this insider component G multiplied by the transpose of the matrix X of our predictors. Here we can build our matrix G. So it depends on how many predictors you have. If you have m predictors, you can build this matrix here. It is a matrix of m plus 1 by m plus 1 dimensions. So it takes this formula, and you put the corresponded x vector of predictors, which is started by 1 corresponding to the W0 coefficient, and starting to list all of your values of coefficients from x1 to xm, where m is the number of predictors. And you also create the transpose version of the x, which will be with dimensions 1 by 1 plus m. And once you obtain all of these three definitions, the G and X transpose, you can easily compute the Hessian matrix by multiplying X by G by X transpose. And once you obtain the Hessian matrix of a particular instance I, then you can update the Wj such that the Wj will be Wj, the updated value of coefficient equals the old value minus the first derivative of log likelihood divided by the second derivative, which we have computed now, which is called the Hessian matrix. And you can simplify this expression by saying that it is equal to Wj minus h to the power of minus 1 multiplied by the first derivative of our log likelihood function. So this is how you can implement a faster way to compute the vector of coefficients W, and it is very efficient way and very fast way if you have a robust machine that can calculate the matrix formulas in a reasonable time. The last point I would like to talk about today is the multivariate logistic regression, the case where you have more than one predictor. I have mentioned this in the first video, and I would like also to repeat it again for your convenience, that if you have more than one predictor X, all what you need to do is just to insert all of the predictors into the linear function inside your logistic hypothesis. So you can replace the f of x over I and w here with more than one predictor from 1 to k, and also you can use the compact form of the linear hypothesis inside your logistic function as w transpose x. And once you use this formula, you can apply it into your logistic regression program, and you can also make use of more than one predictor in order to enhance the generated classifier. So this is everything about logistic regression I wanted to cover. And again, I will put a link to the implementations of gradient descent, gradient ascent, and Newton's method. You will find the link in the description below, and I am encouraging you to download it, run it yourself, and maybe give me some feedback if you find some issues or some interesting issues for discussion. And thank you for your time.